about proof by contradiction. Now, general path or pattern is the same. If you have to prove a fact that every or all summer days are hot and sunny with blue skies, what would you do? You don't have to take every. If you have to prove that not every summer day is hot and sunny with blue skies, notice the not. That means that negation of this statement. The negation of this statement is can is at least one summer day is not going to be with blue skies. Okay, so as long as you say at least one day of if you can prove that at least one summer day is rainy and cloudy, that has proved this statement wrong. Okay, so at least one day is cloudy and rainy. To prove that there is at least one even prime number, you don't. What you do is you will take this video. In this section, you'll be learning about proof by contradiction. So, the preliminary knowledge that you require for proof by contradiction is, first of all, taking care of the word every or at least. So, in this question, we have been asked to prove that not every or not all summer days are hot and sunny with blue skies. The fact that not every is used, that means that all you have to do is find an example of at least one summer day that is not sunny and with blue skies. Find at least one day that has rainy and cloudy days. So that would have proved this statement wrong. Okay? So all you have to do is find at least one example. In this next example here, it says that prove that there is at least one even prime number. So to contradict this statement, we will assume that for for a contradiction, all prime numbers are odd. Okay. However, then we will see that 2 is an even number. Therefore, the negated statement is false. Okay. So the opposite of all is at least one, and the opposite of at least one involves all. Okay, be careful with that. Instead of all, you may have both in your question. So the opposite of both is at least one. Okay, the negation of both is at least one. So let's look at this example. The general pattern to prove a statement by contradiction is to assume that statement is false, first of all, and then take on some logical steps to show that it will lead to an impossible outcome or an impossible effect that is clearly wrong. Therefore, the original statement must be correct because we assume the opposite. Okay, so let's look at an example. So we're going to take the negation of this example. It says prove by contradiction that there is no greatest odd integer. So for a contradiction, we assume that there is a greatest odd integer. We're going to call this integer n. Okay, and then we will have to follow the logical steps to prove that actually there is an impossibility or a contradiction. How? Yes. Let's see if n is, let's say if n is an integer, and then therefore we can add 2 to it, right? So adding 2 to an odd integer, okay, is going to be n plus 2, which is clearly larger than the original n. Now, if you remember, adding 2 to an integer will leave it an odd number. So n plus 2 is an odd number. Now we have a contradiction that the second odd number n plus 2 is actually larger than the first odd number, which we said was in our very, if you look here, we did say it was going to be the greatest odd number, and therefore this statement must be wrong. Therefore, the original statement that we don't have a greatest odd integer is the correct assumption. So n plus 2 would be an odd integer and is greater than n. Therefore, there is no greatest odd number. This principle is called the Archimedean principle. Okay, so pause the video and have a think for yourself. Here is step one, and then the logical proof is in these three lines, which is step two. Alright, let's look at another example. We go through the same pattern again and again, and after a few times you should get the hang of what's going to happen. In this example, we've been asked to prove by contradiction that n squared is an even. So if n squared is an even number, then n must be an even number. Alright, so to contradict this, we are going to assume that there exists an n which is odd, but n squared is an even number. Okay, so what we are contradicting is that n squared is even. So we are going to say that there exists an odd number here that will result in an even number when it's squared. Alright, so what's the expression for an odd number? Let's keep it odd to be an integer. Okay, this capital N, when I write it with double lines, means that it's a member of natural numbers. That also take k to be an integer. Integer is represented by letter z. That means that it could be minus or plus 1, 2, 3, and so on, but it cannot have decimals. So representation of an odd number is 2k plus 1. Okay, so we are going to call n to be 2k plus 1, and when we square n, that means that we are going to take 2k plus 1 and multiply it by itself, which will be 4k squared plus 4k plus 1. Now we can factorize the 2 out of this expression, the first two terms of the expression, and we will have 2k squared plus 2k plus 1. This is clearly an expression for an odd number because we have factorized the 2 here. This is the even bit, and we added 1 here. So this is an expression for the odd number. So what we started with was an odd number, and we didn't get an even number. Okay, when we square n, we also ended up with an odd number. Okay, this was odd, and we ended up with an odd number. Therefore, we have contradicted the fact that an odd number will lead to when it's squared, it will end up with an even number. So that proves the statement because we have used the contradiction here. So the steps was to say that n is an odd number, and we squared n, and we ended up with this expression. And because n squared is odd, which contradicts the original statement, if n is odd, then n squared can be even. Right? We have answered the question. So let's look at the next example. It says prove by contradiction that the square root of 2 is an irrational number. Now, irrational numbers are numbers that cannot be written as a fraction. Okay, a rational number can be written with the denominator and numerator as both integers. Okay, so integers. So for contradiction, we are going to assume that actually square root of 2 can be written as a fraction a over b, and a over b is the simplest form, in its simplest form. Okay, so then what we're saying is this. We're saying that square root of 2 is a over b. Alright, let's play around with this expression to find some contradiction or impossibility. Okay, notice we are making a false assumption on purpose. Okay, in fact, I know that square root of 2 has decimals in it, but we are making a false assumption on purpose because we've been asked to prove by contradiction. So we're gonna square both sides and multiply by b. Let's see what happens. After squaring both sides and multiplying by b squared, we end up with this expression here. Okay, so okay, you might not see any difference here. Okay, this means that a squared is an even number. See, clearly a squared is a multiple of 2. It has a factor of 2 in it on the left hand side. Alright, and if you remember, a only even numbers after squared will give us an even number. Okay, so this means that a itself is an even number. Okay, so this means that a is a 2n or is a 2. Okay, so under the square root here we are saying that actually there is a 2n that's squared here. Now what that means is that 2 is actually a 4. Okay, so this this 2n is 4n squared. Okay, and if we divide everything by 2 here, b squared turns out to be also an even number. Okay, so this step here showed that a is even. Okay, and this step again for the same reason, because we ended up with a factor of 2, is saying b is also even, and it has a common factor of b. A had a common factor of b, and also b squared. A squared had a common factor of b. So this means that after the square rooting, we will also end up with an even number, and b is even. So what's the contradiction? Well, we found both a and b to have a common factor of 2, but we said that a and b were already in their simplest form. So why is it that now 2 is equal to a and b? So this assumption has come to an impossibility because now we have proved ourselves wrong. Okay, so our assumption that the square root of 2 can be written as a over b is, which has been fully simplified, is wrong. Okay, we have proved this by contradiction. Okay, so pause the video if you don't understand this and think for yourself. Think and try to go through the motions, and you'll see what's happening. Alright, we've got one more example to get through, and this is the final example. Okay, so we've been asked to prove by contradiction that there is infinitely many prime numbers. Okay, yeah, notice the word contradiction here means that we are purposely going to make a false assumption so that we can prove ourselves wrong. Okay, Okay, that's the logical steps that to answer this question. So assumption is that there are finite prime numbers. Let's call the largest p with subscript n. Okay, that subscript is just saying that this is the last prime number I know. Okay, let's say that we basic additions. We've only studied maths for 2 months in our lives, and we only know that prime numbers are 2 and 3. Okay, so we only know two prime numbers. All right, so we are going to I'll call our largest prime number p subscript with the n. We only know this many prime numbers. Okay, we can always multiply all of these prime numbers and add 1 to the final product and find yet another prime number. Okay, so what I'm saying is that if you're not familiar with this expression, is that if you take any two prime numbers and multiply them and after that add 1 to it, you end up with yet another prime number. Okay, so this prime number was unknown to us, but we just managed to find it. Alright, just pause the video and have a go for yourself. Let's say you only know three prime numbers, 2, 3, and 5. You want to find yet another one. What you can do is take these three, multiply them together, and add 1 to it. I guarantee you end up with another prime number. 31 is going to be prime. If you want to try this for yourself, have a go. Okay, so this 7 was unknown to us, but we managed to come up with it. 31 was unknown to us, but we managed to come up with it. So this proves that there is always yet another prime number. But we were assuming that we already know that we already know only there is a finite number of prime numbers. This finite number therefore has been proved wrong, and this proves that there is infinitely prime numbers, as the question asked us to do. So in, we are using proof by contradiction. It's uh, it's these two steps that you always take. You are going to make a false assumption, okay, or make an assumption that is opposite to what you are asked to prove. You negate the statement and you prove that the negation is wrong. Okay, so good luck practicing, and I'll see you in the next video.